Hello and welcome to this video on how to show a causal effect. My name is Geiser. I'm an instructor with QuantFish. One question that researchers often have is, how can I show whether a variable x causes a variable y? And so that is the question about a causal effect. Does variable x cause variable y? For example, does smoking cause lung cancer? Or is there another reason, another cause for why people develop lung cancer? And so what I want to address in this video here is the question of how can we establish causality in research? So how can you be sure, or relatively sure, let's say, that the causal direction is in the direction from x to y and not, for example, in the direction from y to x, or that x and y are caused by another variable, let's say z, that is responsible for both of them. So how can we show this? And so the first thing that we need to understand is, what are conditions for causality? And there are three conditions that need to be in place for us to state, or for us to claim, that x causes y. Number one, temporal precedence. X has to occur before y. So x has to be there first, meaning smoking has to be there first, and then subsequently lung cancer would occur as a result of smoking down the road, maybe many years after people started smoking. So that is a very, very important condition for a causal effect, that x occurs before y. If x were to occur after y, it couldn't be a cause of y. So that's very logical and very easy to understand. Second, there has to be an association or correlation between x and y. If x is not correlated with y, it means there's no causation. If they're unrelated, that shows you x cannot be a cause of y. If smoking is uncorrelated with lung cancer, meaning if those people who don't smoke develop lung cancer at the same rate as people who do smoke, then it means x, or smoking, cannot be a cause of lung cancer. And then third, and that's the most tricky one, isolation. There can be no other explanations or no other potential variables that explain the x with y relationship. And that's a very important point that is not met in many studies. Many studies, as we will see later, do not satisfy this condition of isolation, according to which there couldn't be any other variables that might be potential alternative explanations for an association between x and y. We call those variables that are potential, or that provide a potential alternative explanation for the xy relationship, confounders or confounding variables. And that's something that we often have to deal with, especially in research that is not experimental, as we will see later. So those are three very important conditions for causality that we need to know about and we need to understand. Otherwise, we can't understand which research design is actually suitable to show a causal effect. So what is the most suitable design for showing causality, or that x causes y? That would be an experimental design of some sort. There are different experimental designs. What do experimental designs have in common? One thing is that in an experiment, we manipulate the independent variable x, or the hypothesized cause of an outcome variable. So in this case, in our example, we would have to manipulate x, whether somebody smokes or not. So we'd have to assign people to groups where there's one group of people who smoke and another group who don't smoke. And that already shows you that experimental designs are tricky, because we can't really do that, right? That would be unethical to ask people to start smoking because we know, or we're pretty sure, it's not a good thing. So randomly assigning, or assigning at all, people to conditions of smoking versus non-smoking could be very problematic. So an experimental design for this example actually may not work at all. But that would be, so to say, first of all, an important step is that ideally we would manipulate the independent variable x, the variable that we think might be a cause of our variable y. And then subsequently, we would measure our outcome variable or dependent variable y, in this case whether people develop lung cancer or not. So in this case it would be a binary outcome variable, cancer yes or no, but it could also be a continuous variable, so the degree of disease in some way, so the severity of disease, for example, or some other outcome that is a continuous variable. What is ideal is if we can randomly assign people to the conditions of X, meaning we would have a group of people and we would randomly assign them to a smoker and a non-smoker group. And again, this shows you that that is not always possible, because you couldn't really do that. You couldn't really tell people, oh, you ended up randomly in the smoker group, so you now have to start smoking. So perhaps you'll find volunteers who would do that, but then still the question would be, is that an ethical thing to do, to make people smoke when we know this is really bad for your health? But that would be ideal. Now, why is it ideal to randomly assign people to conditions of X? This has to do with the third condition of causality, which hopefully you'll remember. It was isolation. Isolation means there cannot be any other variables that could be potential explanations for the XY relationship. So no confounding variables. And that's what randomization does, is it makes sure that those potential confounders are equally distributed across the treatment and control group. So if we have a smoker and a non-smoker group, then if we randomly assign people to those groups, then we could assume reasonably that those confounding variables would be the same, so to say, in the smoker and non-smoker group. So they couldn't have a correlation with the outcome variable at the end, because they're equally distributed across those different conditions. So for example, people who are already more unhealthy at the beginning of the study, they would be equally likely to end up in the smoker group as they would be in the non-smoker group due to randomization. So you could expect to have an equal number on average of people who are already more unhealthy at the beginning of the study in both those groups, and there would be no correlation later on between being unhealthy and developing lung cancer, because that would be something that would be equally distributed across the two groups, so there couldn't be confounding in that way. So that would be ideal if you can randomly assign people to X conditions, then manipulate X, and then measure the dependent variable Y. Let me show you an example of how this can be done. This is often done in so-called randomized controlled trials, or RCTs. And so here is an example of such an RCT that is called a pre-test post-test design, where first of all we have random assignment RA to two or more groups. In the simplest case, just two groups, G1 and G2. G1 would be a group that receives treatment. So in this case, let's say smoking. And so they would be tested for lung cancer before the treatment to make sure that, or whatever the outcome variable is, that they don't have this already, or that we know what a certain level is of that at pre-test. And then they get the treatment. In this case, they start smoking. And then at some point we do the post-test to see how many people in that group got sick. And then in the second group, we would have a pre-test as well. And then we would administer no treatment or a placebo treatment. So in this case, people wouldn't smoke. And then they would also be post-tested after a certain phase. So you can see that this design satisfies the condition of temporal precedence, because it's a longitudinal design where we have a treatment phase or placebo phase, and then we measure at the end. So later we measure the outcome variable after administering X, the treatment. And then also this does allow us to study association later on, because we can later correlate the outcome variable with the conditions of X with the groups. And it also satisfies the condition of isolation because of the random assignment. So this is a strong design. It's a strong research design, experimental design for showing causal effects, because it satisfies those three conditions for causality that we discussed earlier. Now, why do we have a pretest here? You can also do this design without a pretest, but it is advantageous to have a pretest because this allows you to do a randomization check. Because when you have a pretest and you measure a bunch of variables before the treatment, you can make sure that really the groups do not differ in their average, in their means across those confounding variables, and that they also don't differ in their means on the outcome variable before the treatment, because if they happen to be already different on the outcome variable before treatment, then that could mess up your whole study. So it's like a randomization check to have a pretest, and that is therefore a useful thing to have. But there are also designs with no pretest where you administer the treatment right away to those two randomized groups and then you only do the post-test. However, then you have no control over whether the groups already differed before the treatment. Now, this is a dilemma though, because the pretest can also be problematic. So it could potentially mess up your results, because sometimes the pretest is like a treatment already, because people already know then what the study is about. And so maybe doing the pretest alone could have an effect. For example, if you measure a treatment for improving abilities, such as spatial abilities, and you do a spatial ability test as a pretest to have a randomization check at the beginning of the study, then the spatial test that you administer at the beginning of the study could be a mini treatment. So it could already train people to be better at spatial abilities. And so therefore a pretest can also be problematic. And therefore there is another design that's called a Solomon 4-group design that's considered one of the strongest experimental designs for showing causality, because it does take this into account, the issue of a potential pretest effect, by having 4 groups. So once again, we have random assignment, but this time to 4 groups. And so in those 4 groups, we have, first of all, the same 2 groups that we had previously in the pretest post-test design, where they take a pretest, then they take the treatment or placebo, and then they have the post-test. But then in addition to that, we also have 2 groups where we don't have a pretest. So they are the same regarding treatment versus no treatment, but there's no pretest in group 3 and group 4. And then that allows you to examine a potential effect of a pretest, because then you can compare group 1 with group 3 and group 2 with group 4 to see if they differ and if there's any effect of that pretest. So that's a very, very strong design for causal inference, because it has randomization, it has temporal precedence, you can look at the association between X and Y, and you also have control over randomization, whether that worked, and you have control over whether there's a pretest effect that may have influenced the results. Now, unfortunately, we can't always do experimental designs like that, and the smoking example is actually a good one, because you can't really assign people at random to smoking and non-smoking groups. So that would probably not go through an ethics approval committee or an IRB committee, because they would say, hell no, you can't really make people start smoking. It's addictive, it's really bad for your health in multiple ways, and so therefore you couldn't study it like this. And that's the case with many types of X variables, that they simply either are not ethical to be manipulated in an experiment, or simply we have natural groups that we can't assign, like for example gender. Males and females, those are naturally occurring groups. There's no random assignment to those groups. And therefore, when we have something like that, we use quasi-experimental designs. Now, quasi-experimental designs from a causal inference perspective are suboptimal. There's no question about that. They're not as good, not as strong as experimental designs, but they're often the only choice. So in a quasi-experimental design, you have groups that are pre-existing, or you have groups that are self-selected. So for example, you look at smokers versus non-smokers. So you examine people who already smoke. So you don't have to make them smoke. They already are smokers. And you compare them to people who don't smoke. Now, why is this problematic? Because those designs lack random assignment. Those people who smoke they already did that, and they may be systematically different from those people who chose not to smoke. So they might differ on confounding variables, such as, for example, they may be more stressed. So they may be under conditions where they're already more susceptible to disease, to cancer, maybe because of stress, and that's why they smoke. And so then maybe it's not the smoking that causes them to develop cancer, but rather it's the stress. And those people who don't smoke, maybe they're less stressed. Or they are naturally, smokers may naturally be more susceptible to addiction. So they may have all kinds of other characteristics that may be addiction related, that may be problematic, and may cause other problematic behaviors that we don't know about, and that cause them to also be more likely to develop cancer, other unhealthy habits such as eating junk food or being exposed to maybe unhealthy hobbies or something like that. So those are all things that are problematic with quasi-experimental designs, where we don't have random assignment because there could be systematic differences between those groups that we don't know about. So the best thing that you can do then is think about what potential confounding variables could be and measure them. So measure as many potential confounders as you can, and then use them in analysis of covariance, for example. So in a type of statistical analysis that allows you to control for potential background variables, for potential confounders. And there are all kinds of statistical techniques that allow you to do that. However, it's imperfect. It's not as good as random assignment ever. So the statistical control will never be as good already, because you are probably not able to anticipate all the variables that may be confounding variables. So some of them will remain unmeasured, will remain uncontrolled for, and therefore this will not be a perfect causal inference design, because the condition of isolation will probably not be perfectly met. Another thing that's also often done is the use of observational or correlational studies, where you don't have any groups. So you simply correlate, or you may not have any groups, so you may simply correlate variables with one another. So frequency of variable X with a variable Y, or a bunch of variables. And so you simply measure variables and you correlate them and look at association. Now this is a very weak design, especially if it is cross-sectional. So meaning if it's not longitudinal, where X occurs or is measured before Y, then this is a very, very weak design, because all you can show with a design like that would be association. So you would only be meeting one of the three conditions for causality, namely that X and Y are associated, are correlated. You could examine that. You could calculate a correlation and see, is it different from zero. Now, we all probably have heard the phrase that says correlation is not causality, and that's true. So correlation alone does not prove causality, because correlation could also occur if Y causes X rather than X causing Y, or if Z causes both X and Y, or other confounding variables. So association alone is not a sufficient condition for causality, and so a correlational study that is cross-sectional lacks the temporal precedence condition and lacks the isolation condition also. Now, the best that you can do is at least do a longitudinal observational correlational study. Then you at least could be meeting this criterion of temporal precedence. And again, you could measure or try to measure confounding variables and then include them in your statistical analysis as statistical control variables, or covariates, as we say, in an analysis of covariance, or a regression analysis where you have additional predictor variables. So that way you could try to fulfill this condition of isolation by having all those confounders. However, it is difficult, because again, you will not be able to measure them all, and or the statistical control model may not be perfect. So this is, so say, the problem with non-experimental designs. However, oftentimes this is the only choice that we have, because we cannot study, for example, gender groups by random assignment. We could not randomly assign people to conditions such as smoking or non-smoking or other hazardous behaviors that would be unethical to expose people to. And so therefore there are situations where we have to resort to quasi-experimental designs or observational correlational studies. I hope you found this video useful to learn more about causality. If you did, please subscribe to this channel, check out the resources in the description, and I'll see you next time.